All right, hello everyone. Thanks a lot for coming. I'm Brill. I'm currently a research affiliate with Principles of Intelligence, also known as PIDS. Today I'll be talking about some work that I've done that's part of the conference proceedings, which is a model for scaling laws of general intelligence. And so the basic idea that we'll be exploring in this talk is the idea of the scaling hypothesis, which can be articulated as saying that the secret of AGI is that intelligence is just simple neural units and learning algorithms applied to diverse experiences at a currently unreachable scale. So the idea is just that you have some collection of neurons and you train them up on diverse data at large scale, well, that will unlock AGI. And this is the basic idea that has motivated pretty much the vast majority of AI investment and research over the past 5 years or so. And so we can ask a number of questions about this. First of all, is this even true? I think the jury's still out on whether this will really work. And maybe from a quantitative point of view, can we get a little more granular? What are the conditions and to what extent would scaling in this regime yield general capabilities over, for example, just a huge collection of narrow task-specific memorization? And are there factors that can affect this? For example, we said diverse data. Well, to what extent does just changing the diversity of the data affect whether we learn general capabilities or not? And we can also say, are there any properties of the model that might matter? A very simple thing is the expressivity of the model. If it can model more complex functions, does that change anything about what might be learned? And so those are some of the questions that you might want to investigate. Another important thing that we want to know is, can we relate the measurable, observable properties of training to the capabilities that are learned by the model? So we have things we know, the compute used, the size of the model, the size of the data set, and we can, as I'll talk in a bit, say, what is the loss that we get? But then how does that relate to what the actual capabilities of the model are? And a priori, you could achieve this exact same performance, but through many different strategies. And so it's not really clear, there's a missing link here, and it's not really clear how to fill that in. And that's something that we're interested in. This plot here is actually from an AI governance paper. So this is a question not just of scientific interest, but also of possible practical use, although here at Iliad, we don't necessarily need to care about that. And finally, are there any universal qualitative statements that we might be able to say about the emergence of general intelligence, general capabilities, or about general intelligence, its relationship with scale? And one of those is maybe the idea of emergence. So this plot is from GPT-3, and showing that at a certain scale, suddenly the performance of few-shot learning suddenly jumps up from effectively 0 as it had been. And is there any simple story that we could say to explain this? Now, this idea of emergence is something that's been studied a lot since this, and lots of papers finding in different scenarios and casting doubt on the whole concept and so on and so forth. We won't be delving into those details. In fact, we won't really be answering any of these questions in real life. So what we'll be doing here is studying a deliberately simplified toy model that will represent our key hypotheses. We'll study it quantitatively, and then by doing so, hopefully gain some intuition that could help us understand what might be happening in real AI systems. And as a little preview, the basic idea is that we'll think of an AI system as optimally allocating its model capacity between circuits that either provide memorized task-specific features or that implement general-purpose capabilities. And as we'll see, this optimal balance can change with the scale of the model. Okay, so now I'll say a few words about the basic concepts that go into what we're talking about. And one of those is the empirical phenomenon of neural scaling laws. So this is the idea that as we in deep learning, as we scale up the size of the model, the performance gets better in a predictable way, generally following a power law. And so we could think of the scaling laws in the data set size, we'd be measuring tokens. In the model size, just as a number of parameters. And then for a given architecture, then we can also say, well, what is the scaling law in compute as a derived quantity? And that's something that's of practical importance as well. So this finding shows this is has driven so much of the investment and scaling up of AI systems, and it is a really cool thing. It seems to be a somewhat universal phenomenon that very similar scaling laws are seen across different architectures. There's scaling behaviors in different modalities and data sets. And this suggests that it's not some specific property of one particular architecture, but may be connected to universal properties of natural learning tasks. There are some important caveats that I think it's always important to keep in mind. One is that these scaling laws are really more empirical, engineering measurements, I would say. That you train some specific model on a specific task, and there's no particular reason to think that the way that we're optimizing deep neural networks today is the truly optimal way to do it. You could pick some horrible hyperparameters and get any kind of loss curve that you want. But one thing that we can say is what we get at least is a bound on the optimal scaling, because the best you can do, the optimal performance, which is something that might be theoretically tractable, that has got to be at least as good as what's already done. And then one other thing to keep in mind is that these are somewhat abstract. So when we talk about scaling in data, we don't really say what the data is. When we talk about scaling parameters, we don't really say what the architecture of the model is. And then also we're talking about simple training or a supervised or self-supervised pre-training task. Nowadays, for a real AI system, there's many layers of fine-tuning and scaffolding that are built on top of that, and that we won't be discussing. So this is a empirical finding, and so it's of interest to say, well, theoretically, why might these scaling laws exist? So I'll highlight a few different stories that have appeared in the literature to try to explain their origin. One is this idea of manifold approximation. And so the idea is that natural data, maybe we naively represent it in some high-dimensional vector, but in reality, it's confined to some low-dimensional manifold embedded in the input space. And so then here the idea is that we have some continuous function that we're learning on some low-dimensional manifold, and we have non-parametric function approximation with n degrees of freedom, which is a reasonable thing to say about a neural network considered as a non-parametric function approximator. Then because you cover that manifold with your degrees of freedom, then the loss will scale proportionally to n to an exponent that is inversely proportional to the manifold dimension. And here, the degrees of freedom is a measure of the model size. It actually stores exactly the same if you think about the data set size as well. And then in this constant, in the exponent, it's to the minus constant c over the dimension, and this you can interpret this constant c as a measure of the model expressivity. So if your function approximator is a piecewise constant approximator, then this would be greater than or equal to 2, and if it's a piecewise linear function approximator, which a Brill neural network would be, then it would be greater than or equal to 4. And if we say the function that we're trying to learn is just a generic continuous function, then you can ignore these inequalities and it just saturates as inequality. And so this is one influential picture. It's very simple and elegant, and it can also, as this paper Bari et al. Shows, you can connect it to some sophisticated treatments with random feature models and things like that. I don't find it totally satisfactory. So one thing is that when we talk about a GPT-5 and it's able to write code and do complicated reasoning and write poetry and play chess, and these seem like a great diversity of tasks where we imagine that the success of deep learning is due to having learned good features to solve these tasks well. And in this story of just covering one particular manifold, it doesn't really seem to speak to any of that. The idea of a diversity or feature learning, it seems a little too impoverished. So you can also think about other simple toy explanations that maybe do of scaling laws that do have this idea of diversity of tasks. And one simple one is to say that, well, maybe we can think of in a super spherical Cow way that the data distribution consists of discrete atomic tasks, and then their importance or their frequency is just distributed as a power law. And so the idea here is that the importance of each task is proportional to its rank k, where rank here just means 1, 2, 3, the most important task, the second most important task, the third one, to an exponent, we can call it -1 plus alpha, so it's just some exponent. And then the loss will just reproduce this power law, and so we get a scaling law of model size to the minus alpha. And so this is another different way to think about what data might look like. And here the downside, this is maybe a little too simplistic, that each task is just like this atomic unit with no kind of substructure at all. So maybe a way to combine these two stories is we can say, well, maybe we have multiple data manifolds of some intrinsic dimension in the different sizes, and we can say we have some power law distribution of these manifolds. And so a way of unifying these two pictures. So we'll consider two different models. One will say there's a single task with one manifold. That's just the original manifold approximation story that I mentioned. And then we'll also say that we have a power law task distribution where we have manifolds with a rank size distribution that is this power law. And each of these represents a distinct task, and it has some separate target function that's to be learned in the manifold approximation way. And so this is a simple model. In fact, you can motivate this, or I have motivated this as a natural data model, which using percolation theory in some previous works, including at the previous iteration of Iliad. But we don't need to get into any of that, and that's not really necessary for our purposes. We're just going to assume this as a simple data model. Good. And so that's the data. And so now, how can we think of the AI system that's supposed to be learning this? So here we're going to build on this fundamental hypothesis of mechanistic interpretability, which is the idea of circuits. And so this idea is that the proper way to decompose a neural network is not into the individual neurons, but into what we call circuits, or some kind of subgraphs that implement meaningful mechanisms. And this isn't just made up, but in reality, people have actually found the circuits. This plot on the right is from Anthropic, and it's a diagram showing a circuit that they identified in a large language model. Now, this is a very active research area, finding these circuits, and it's ongoing and still quite messy. We're just, as I'll say in a moment, we'll just be seeing a very simple stylized picture of what a circuit is. Yes. So, okay, good. And so our AI system, here we're going to be thinking about a standard machine learning setting of regression on some supervised or self-supervised task. And we're going to assume a stylized AI system that is n units of model capacity. And so we're going to keep this as a totally abstract notion, and the model capacity is just some fluid that can be used for different purposes. But you could think of this as connected to the number of model parameters, or the complexity of the model. And of course, it's an ongoing theoretical work to connect the true capacity of the model to the number of parameters. And now our key assumption is that the model be capacity constrained. So it has access to unlimited training compute, so it's going to train fully to convergence, and there's unlimited training data with which to do that. And so the constraint is the finite amount of model capacity to perform the training task. And what is that going to be used for? It's going to be used to optimally instantiate circuits from some latent population of circuits that might be potentially relevant. And in our model, we're going to assume a super simple model of what a circuit is. We say a circuit will consume big N capacity, and on each task k, we provide little n degrees of freedom. So that makes sense. It's a little function that has some capacity cost, and it can give us some degrees of freedom. And so we can, given that, another thing that we could say, we can define the efficiency of a circuit, say on a particular task or set of tasks, as just little n over big N, the number of degrees of freedom provided over the capacity cost. And we'll assume, make a further simplification, that there's exactly two kinds of circuits available. There's feature circuits and general circuits, and now I'll say what those are. So a feature circuit computes one feature that's relevant to one task. And by feature in this context, I mean something in like the classical machine learning idea of a feature. It's like some basis function or memorized example, something like that. And we'll say that all of these features are identically generic, and so we'll choose units so that each feature circuit costs 1 unit of capacity and provides 1 degree of freedom on its particular task. And then we can just say, for some task k, we can write n sub k is just like the total number of degrees of freedom provided by a feature circuit for that task. So the shorthand. So the kind of circuit that might be more interesting is general circuits. And so we'll say that that's a circuit that implements a capability that's going to be relevant to all tasks. Now, of course, we all know that there's a fully agreed upon definition of general intelligence and AGI. Unfortunately, I ran out of space to include that on the slides. But heuristically, we can say like a general capability is something that is helpful maybe for any logically consistent and physically plausible task, but doesn't depend on any contingent information about them. And so I'm thinking about these general circuits as a model for things like that. So some examples of what one might have in mind: something that does logical inference and probabilistic reasoning, in-context learning or meta-optimization, which would work for would apply equally to any context or situation. Situational awareness, including self-knowledge. Like if you're an agent, like any situation you're in is going to have you in it by construction. So self-knowledge would account here. And maybe something, like maybe there's this idea that there's some core knowledge of things like objectness or number that just in any physical, plausible scenario is going to be relevant. So maybe that would be something that would count here too. So from this list, I think it's clear that these are very disparate things, that they might vary widely in complexity and utility. So there's not really some obvious efficiency scale for all these different circuits. So instead, we'll assume a super simple model. We'll say there's some, at least in some regime of applicability, like the simplest model we can pick is like a pure power law, which is scale-free. And that's an approximation, and we're not claiming that that's like exactly true, but it's a simple model that is very reasonable. And so we'll approximate the population of the general circuit marginal efficiency as a power law. And so that will be here epsilon naught. So we have two free parameters now. So epsilon naught is this prefactor that will just set the efficiency scale of general circuits relative to feature circuits. And then gamma is the exponent that will control how fast the efficiency falls off. And those are free parameters. Good. All right. So now we can start saying a few things. So we can ask in this model, how do we measure the extent to which the AI relies on general capabilities, which is kind of the question that we might want to ask. So we can attack that in a few different ways. One is we can define this capacity fraction, which is the capacity of the neural network that's devoted to implementing general circuits. So that would just be the total capacity consumed by general circuits over the capacity. And we might then also want to know, like on any given data point or input, what's the fraction of the degrees of freedom applied to it that come from these general circuits? And that's maybe a measure of to what extent the model in its predictions is relying on these general capabilities as opposed to more narrow task-specific features. And so that can be shown here. So if we have multiple tasks, well then the degrees of freedom from general circuits are going to be the same always because those apply equally to all tasks. But then the denominator might be different for different tasks which have different number of feature circuits. So we just take the expectation value over all of the tasks. Right. And I think one way to visualize what's going on is this idea of a circuit efficiency spectrum, which was coined by Dmitry Vaintrov, who, I don't know, he's not in the audience, but he's here at the conference somewhere. And we defined the efficiency before. And so you can just make a plot of, on the x-axis is the capacity cost, and on the y-axis is this degrees of freedom. And so the slope, if you plot all of the circuits, the possible circuits that you might instantiate, then the slope here is going to be the efficiency. So if you think about like a rough heuristic picture where the loss is just proportional to the degrees of freedom, then you would like, if you're at convergence, then you would just learn the most efficient circuit and the next most efficient circuit and so on. So kind of like the slope will like slide down like that, and that will just control which circuits that you learn. Does that make sense? So you just learn from the most to least efficient. Now, in this picture, it's more complex than that because different circuits can operate on different subtasks. So there's going to be interactions between the circuits, and the loss will be a nonlinear function of n here. And so it won't just be the simple picture where like this, you count 1, 2, 3, the most efficient in the next one, but it'll be a more rich dynamics than that as scale increases. And so we can make these diagrams for the efficiency spectra for our two scenarios that we're going to consider, the single task and the parallel task distribution. These orange circles are it's just a cartoon representing the general circuits that have some power law and efficiency. And these blue crosses are the feature circuits. So for a single task, you have your general circuits, and then I guess this is supposed to be the point 1, 1, where all the feature circuits are just superimposed at that point. If you go to consider now power law task distribution, the general circuits look exactly the same, so they're going to stay on the left and the right. Now the feature circuits are a little different because you have your feature circuits for like the rank 1 task and then the rank 2 task and so on and so forth. And so this diagram encapsulates our assumptions about what the possible circuits that the model could learn and will optimize and do so optimally. All right, so I guess those are the yes. No, this is a cartoon that represents the assumptions that we're making in this format. And yeah, but that's a good question. And it's worth thinking about, certainly will not be addressed here, how you could maybe measure something like this in real data. I don't know exactly how to get it from data, but it might be possible from, let's say, examining the trained AI system through some interpretability that you could recover backwards that way. Okay, so now we can start doing some math. So we'll start as a warm-up with the single task data distribution. And so the idea here is it'll be a constrained optimization problem. So the loss is just going to be the sum of the degrees of freedom from the feature and general circuits raised to this manifold approximation power law. So that's the exponent there. Subject to the constraint that the total model capacity has to add up to whatever the capacity of the model is. And here, for this is just like from the integral of that power law assumption for the general circuits, and m is just the constant that it comes from the other constants we already found. So we can do this using Lagrange multipliers, and there's Lagrangian. So there's 3 possible cases. The model might learn only feature circuits, only general circuits, or both. So you can call those case F, G, and FG for shorthands. And so then, for some given scale, whichever case is going to minimize the loss, that will determine the overall. So the approach is just to solve these separately, and then we take the minimum of each one. Now, for this is like a super simple Lagrangian, and I mean, you can look in the paper for it is done, like solved out, but it's not really necessary. I think it just intuitively, you can think about what would happen. So if the feature circuits are more efficient than the most efficient general circuit, then there's no point in ever learning any general circuits. You'll just learn feature circuits, and the number of general circuits will be 0. On the other hand, if the general circuits start more efficient, then the optimal thing to do is to learn them until you hit the point at which the feature circuits are once more most efficient, and then you just learn those until the end of time. So what we see is in this single task data distribution, there's a hard bound on the amount of general capabilities that you would ever learn. And that bound may well be 0. And so like the total ng here is a constant for a large n. And this kind of makes sense like intuitively. If you have a single task, then it makes sense that learning some general capabilities wouldn't really need so the more interesting case is when we have this power law task distribution. So now we have a diverse set of tasks that we're going to learn. And so the loss here is now the sum of the losses from all these different tasks weighted by their size or importance. And again, we have the capacity constraint. And, well, naively, there's like an infinite number of variables now we have to optimize over. So nk goes from 1 to infinity plus ng. And so we can bring in some few intuitions here to make this into a more solvable problem. So first thing to realize is that it's never going to be optimal to assign your DOF to like a less important task. So like you're always going to assign DOF to like some subset of the most important tasks, like the ones that are the largest size or smallest rank. And so we so they'll be assigned to this first one up to some grade. So then we can make it an ansatz, which is that the distribution of these MKs is a power law with an index that we can call b minus 1. And good. And then we can bring in our second piece of intuition, which is that at equilibrium, the marginal loss reduction from assigning more degrees of freedom to any task has got to be equal for all the tasks for which we've assigned any degrees of freedom. And so that allows us to solve for this exponent here and the nk distribution, which is shown here. So that is going to depend on the ratio of the task distribution exponent and the manifold approximation exponent. So that exponent b will control the dynamics of what we see, and that's important for determining the regime of the model that we're in. And we still need to solve for 3 variables. We still need to solve for ng. We need to solve for a, which is this prefactor here, and the k-break, the break rank. And to do so, this is Lagrangian. And we have the same 3 cases as before. Features only, general circuits only, and both. For the general circuits only, it's easy to solve. The others don't have any closed form solution. So to proceed, we can study some approximate analytical solutions in limiting cases, which depend on the value of b. And we can also solve these equations numerically using gradient descent. I'm not going to walk through these analytical solutions. You can read the paper. Instead, I'll just show the plots of the numerical solutions with the analytical approximations overplotted, and talk about some of the lessons and takeaways that we can learn from the results of the model. So the first thing that we see is that this is a plot of the model size and ng, degrees of freedom from the general tasks or general capabilities. And we see that there's no absolute bounds on the amount of general capabilities learned now that we're in this power law data distribution setting. And so that will just increase with no bound, which is a sharp contrast to the single task case where there was a hard bound. And so this means that general capabilities at scale result from the require training task diversity. Interpretation here. And another key finding that's also visible in the same plot is that general capabilities emerge abruptly. So for depending, there's a threshold model scale below which ng is just going to be identically 0. There's no general circuits, and that you're learning only feature circuits. But at some point, at some threshold, which depends on the exact values of the parameters, then there's a transition to also learning general circuits at the point that you learn that first general circuit. And so ng here shoots up from 0 to some finite value. And this is like a really simple model, but has this property where you have this like something that looks like this idea of emergent capabilities in some model scale. We can look at the loss curves here, and so this is the This is scale, now it's lost on the y-axis. And something that we can see here is, well, it makes sense that general capabilities are learned. Why? Because they unlock faster scaling laws. And you can see here, for example, it's easy to see on this red curve, where I've just added a dotted line, extrapolating what would happen if you could only learn feature circuits. But because general circuits are learned, it's a much steeper scaling law. And this makes sense because general circuits can decrease all tasks lost in parallel, as opposed to only one task. So there's another, I think, interesting finding that we see, which is that even though the amount of general capabilities always increases in an absolute sense with scale, it decreases proportionally. So this is these metrics that we defined, the capacity fraction and the DOF fraction. And we see that at some scale, right, we have this emergence, so it shoots up to some finite value, but then afterwards, as the scale continues to increase, it will decay slowly. And this can be interpreted as saying, well, it's because as the marginal efficiency of the general circuit population decreases, then the model is going to rely on adding them less and less, and the relative contribution of the general circuits will decrease too. And so what this means is, as scale, there's going to be like a gradual decoupling of the loss improvement with how much of that can be understood as being attributable to general capabilities. And then a few things we can also look at. We can examine the effect of some of these parameters of the model. So one is the data diversity. So here on the y-axis, this is again the DOF fraction, and then now the x-axis is alpha, which is the task distribution exponent. So if that's close to 0, that means we have essentially like a flat distribution, and it's highly diverse, and the DOF fraction shoots up. As that gets smaller and smaller, then you have a steeper task distribution, and it's like more akin to just like if you have a single task, and the DOF fraction approaches 0. And I think this general finding is very intuitive. This makes a lot of sense. Although it's, to me, I was surprised by how strong the effect was. I think this is a very, it's very clear looking at this plot that even relatively small tweaks to this data diversity can have a big impact on to what extent the model learns general capabilities in this toy. One thing that you can also note here, this is varying the value of gamma of this the general circuit distribution, and at least qualitatively, it has very little effect, showing that this is pretty robust to that free parameter. And then the last finding here is we can also think about the model expressivity. What effect does that have? I think that's it's not clear at all, a priori. And again, what we see, though, is that as you increase the model expressivity, then it also enhances the general capabilities, but this time like much more moderately and shallowly. And I think the interpretation of this is that you have a very expressive model, you're able to learn faster, and so with a given capacity, you're able to effectively see more tasks. It's reasonable to model more tasks, and so it's a way of like enhancing the effective data diversity. Whereas if the expressivity is low, that decreases the effective data diversity. Yeah. All right. So I guess I have a few more slides. So we can talk about the limitations of future directions. So the idea here is that we studied a highly simplified toy model, and by doing so, we can, from a very few abstract assumptions, we can maybe try to gain some universal insights. But of course, we can also say, well, maybe you don't believe the assumptions. And so then this is a good way to examine if we change these, what could happen from building on this work. So I'm going to highlight some of the key things that we assumed. One is that the model is purely capacity constrained. And I think this is a reasonable idea, thinking about an agent that's supposed to be modeling the entire world, that for any finite system, the world is going to be bigger than you. And so that's a way of justifying that. If we're talking like a more realistic setting, like an existing AI system, of course, in practice, many other constraints come into play. The amount of training data the available compute, of course, is quite limiting, maybe the amount of context. And so you could think about, if you include other constraints, how does that change the behavior? And the other key assumption is we're talking about an optimal model at like convergence. At the, that would be like the end of training. And of course, it would make this picture much richer to bring in non-equilibrium behavior. For example, like what are the dynamics of training? And of course, that's what many people study. So this is a complementary approach. And so you can think about, well, are there like issues about the learnability of circuits that come into play? Another thing is we talked about model capacity, measured in degrees of freedom at quite abstract level. So I think an important task for theory is to, and people are working on this, is connecting these notions to like the concrete measurable things, like the number of model parameters. And then finally, this was brought up before, we had these three parameters about the circuit population, and so we could think about other strategies through interpretability to maybe develop better models and to measure what the values of the parameters are. Okay, so in conclusion, here we examined a toy model that of a scaling of general capabilities, and by doing so, the hope is that we can clarify concepts and predict some universal phenomena in a very universal abstract way. I think an important thing to realize is that if we want to bridge like notions of scale and loss with what the capabilities of the model are, we need to have some kind of mechanistic model about what is going on inside, in this case, like what the circuits are. And I think the intuition from the picture that we painted is that memorizing narrow features are constant complexity, but general capabilities are gained in descending efficiency order. And what this means is that we see the effects, I think sort of the key effects are that general capabilities emerge abruptly, but then decrease proportionally with the model scale, so the loss and the general capability so that's all I have for you today. Happy to take any questions. Thank you.
Thank you for your talk. I'm a little bit confused, like you showed on your plots on the y-axis, usually NG.
Mm-hmm.
How do you measure that?
Like in a real AI system.
Like in a toy model you use, how did you measure NG?
Okay, so this is, I'll just bring up one of these plots, like this, for example.
Yeah, exactly.
Yeah, so this is, it's numerically solved, and so then you can just compute it from the variables, the optimized variables. Does that make sense?
Then I don't understand what you're saying. NG is the number of general tasks the model can solve, right?
So that is defined, so that metric is defined here. And so NG, that's one of the parameters that we solve for. In some limited cases, we can solve that analytically. But in general, we can solve it numerically. And then you can just compute. And then also all of these NF are also solved for. This is what we call like NK, this function of K. So then those are all solved for, and so you can just compute this.
So it's correct with predictor.
Yes. Yes. So this is all totally theoretical, and like I said, this is like a toy model that we're solving.
So the consequence of predictions of the theory.
Yes. Yes.
Okay, I thought you measured that.
No. So none of this, what I showed, is like an actual neural network that was trained. It's solving these equations.
Okay.
How do I say that?
Sorry, could you please repeat the question?
My question is along the calculations. Are they done and basically by the relative?
Yeah. So these equations, it's like this is deterministic because we're assuming that we're just out. Yes, the interpretation would be something that would be an expectation value over some data set. However, the equations that we're solving itself, this is deterministic. Right, so I guess there would be two sources of variability. One would be the training set size and one would be the test set size. So here we're assuming infinite training set, so the variability is 0. But of course, if you back away from that and consider finite data, then yes, then the variability would matter quite a bit. And of course, you also can think of the test set. Here implicitly, we have an infinite test set. But if it's maybe if it's known to be finite, then there's other things like the more rare test would be higher variability. Yeah.
I wonder if this could be used to generate some experiments to do on actual model training, and especially generalizing the task. This still seems very much like the world of abstract tasks or LLM tasks, and it might be interesting also to look for practical tasks, perhaps in a grid world reinforcement learner case.
Yeah, definitely. Right. Here, it's like all thought of, this is kind of the LLM type of framing where it's self-supervised. I haven't thought about if they're, like, how difficult it would be to translate this into, like, an RL type of setting, but yeah, I agree.
Might be interesting.
What do you want to do next? Like, what do you push this research?
Yeah, so I think for me, probably from what I would be most interested in and what's most tractable would be something akin to these first two bullets here, like trying to take this picture, which is dealing with like a full optimalist model of convergence and connecting it up to this like learnability. Like, can you have a more rich picture where you also include not just the model scaling, but like the training steps scaling or data set size scaling, which are a little entangled. And so then you can say, not just at the end of training, but at point in training, what you expect to see. And of course, this would bring in many other theoretical approaches. Yeah, I mean, that has a pretty simple explanation, which is that at some, well, actually this would be a good plot. So, just thinking heuristically, this is oversimplified, but you're going to start by learning like the first, like the most efficient one, the next most efficient one, and so on. So at some point you start by learning some circuits, and at some point the first general circuit's going to be optimal to learn next, and then you learn it, and that's the point that there's this abrupt emergence. And then of course there could be micro emergences, like here again there's this abstraction, and where you're going a little back and forth about is this like a continuous distribution or is it discrete of these different circuits? But you could also say like each individual circuit is one too. That's another micro emergence. Does that answer your question? You can set the parameters such that, like, you can just say the general circuits are far more efficient than any feature circuits, and then of course you're going to start by learning general circuits first. I think just the intuition for why that might be a less realistic model is that like a single feature is just like such a simple thing to learn that it's hard to imagine some very complex like circuit that does something like in context learning is going to be simpler than just a single memorized feature. So that would be the intuition for why you pick those parameters. But of course you can pick whatever parameters you want in the model and the map for yourself is the same.
Model with learn like general circuits, and then learn like all the other like specific feature circuits like going forward. But under the rocking paper, the central element is that it first learns to memorize and then to generalize, and see this kind of phase shift as the general circuits then online. Do your theory like predict this, or like how do you spread these things?
Yeah. So here, what we're looking at is the scaling with model. Any of these plots is fine with model scale. So not overtraining time. So with rocking, we think about as you train for more and more steps, suddenly there's a shift in what you've learned. Here, this is what is at infinite steps, and then you put that in the plot. Then you have a new model at a larger scale, infinite steps, you put that in the plot. So whichever one is ultimately more efficient, that's what's going to go here. And that's the difference between a lot of times we think about what happens over training. So it's just a different limit that we're interested
So training times, switching, which is good.
Say that larger it's a lower proportional over times. Does this predict that larger models in the data training case would learn less efficiently without maybe per train stack or per track fewer circuits?
Yeah, so if you have a more expressive model, you learn more general circuits.
But you were saying that it less proportional to the total capacity.
Oh yeah. Over scale.
In the limit case.
Yeah.
And like, how does this limit case translate to, the practice actually in a scale?
Totally, yeah. So this is not handled here, and now you would need to also have a notion of how fast the circuit is to learn over time. Here we have none of that. So if a circuit is like efficient, but it would take like a really long time to learn, this is like rocking, where the generalizing solution might take a lot longer to learn. It's not included here. And so this is what you would need to do is like to answer that question, you need to also bring in that notion of how fast it is to learn into this picture. The training dynamics? So here, no. So here, this is like, at the end of training, in fact, it doesn't even matter how you train. It could be anything. It could be like, literally in this case, we're analytically or numerically solving some equations. So you don't even assume that it's gradient descent. It's actually more general than that. So you would need to bring in some additional assumptions about training dynamics to say anything like that here. So this would be like this. I think of this as a complementary analysis tool to thinking about the gradient descent. All right. Well, great. So if anyone else has any questions, I'd be happy to answer them. And thank you again.